Hi, my name is Grace. This is my Physics Lab 4, and we're going to be looking at energy of a spring mass in motion. So important concepts for this lab are conservation of energy, this meaning that delta energy is equal to 0, and we'll see how energy is transferred between spring potential, gravitational potential, and kinetic energy. And the forces that are in this lab are spring and gravitational forces acting on the mass. So important formulas are definitely the formulas for spring potential, gravitational potential, and kinetic energy, in addition to our formula for total energy, which in this lab is the combination of the kinetic, gravitational, and spring potential energy. So for our model code, before we move into the calculation loop, we had to define some constants. If you see here on the left, you can see the calculation we used to find the spring constant. And in this case, we use this by finding the oscillation periods from the tracker video. I found the oscillation period in the y direction to be 1.48 seconds. And then we solved for the spring constant by using the formula Ks is equal to 4 pi squared times m over the oscillation period squared. And we found Ks using the y oscillation period to be 7.17. Then using that spring constant to find L naught, we use the formula L naught is equal to the magnitude of the length vector minus the mass times gravity over the spring constant, and we found this to be 0.15 meters. Up here in the top right, using some standard formulas to define L, L hat, and S, and we also define our different energies. So we use the formulas that we discussed previously for the kinetic, gravitational potential, spring potential, and total energy. Down here on the bottom right, we also defined the mass of the ball, which was given to us as 0.402 kilograms, and we also define our initial position vector using the position of the mass from the tracker video, and our initial velocity vector is 0 because the mass starts from rest. So moving into our calculation loop, over here on the left, we use the formulas for F grav and F spring, and our F net is equal to F grav plus F spring because those are the two forces acting on the mass in this situation. Down here on the bottom left, we use just standard position and velocity update formulas so that we update those through each iteration of the loop. Up here on the top right, we actually define our initial energies by, the initial energies are set to the final energies calculated in the previous iteration. And then at the end of the iteration, we update the all of the energies after we've updated the velocity and position, and we find our change in all of these energies by subtracting the initial from the final. So here's our model result. As you can see, the red ball is the experiment and the blue is the model. The red ball's motion is a bit more staggered. That's due to the nature of how tracker uses point mass to track the object's motion. And the model successfully follows the elliptical motion that we saw in the tracker video. So for our graphical analysis, here, this is our change in energy versus time graph. The blue line is changing kinetic energy, red line is changing gravitational potential energy, green is change in spring potential energy, and our orange is the change in total energy. As you can see, the orange line remains constant at 0. This is because energy is conserved and the energy principle is satisfied. As the spring oscillates, energy is transferred between spring potential, gravitational potential, and kinetic energy. And here we have our position versus time graph. The red is the experiment and the blue is the model. As you can see, the red line is a bit shifted. That's because the oscillation periods are a bit inaccurate due to human error. And we also see that towards the end of the time interval, the red line does not oscillate as far in the y direction. This is due to the loss of energy from friction and air resistance. So our difference in our oscillation periods, as you can see here on the left, the x oscillation period is different from the y oscillation period. This is due to the elliptical motion of the mass. You can see it's oscillating differently for x and y. And also the x and y are independent from each other because the oscillation in the y direction is affected by F grav, while in the x direction it is not. And you can see that in this tracker video here. Thank you for watching my lab.